Welcome back to The Explainer. If you're gearing up for that Cambridge IGCSE Computer Science 0478 exam, you are in the exact right place today. We're zeroing in on a critical concept that can literally make or break your code and, honestly, your grade. We're talking about data types and input validation. But look, this goes way beyond just passing a test. These concepts, they're the invisible safety nets of all modern software. A simple mismatch in how data gets handled doesn't just lose you points. Out in the real world, it can ground commercial flights, freeze international banking systems, or completely corrupt a critical database.
Picture this. You open your exam paper, or maybe you're running your final program, and boom, the system completely crashes. Why? All because a user typed the actual word 2 instead of the number 2 into an input box. Let's think about what happens under the hood here. The second that text hits a variable that's expecting a pure integer, the compiler absolutely panics. The memory allocation doesn't line up, the program can't do the math, and it just terminates on the spot. The end user is just staring at a blank screen or a massive error code. It's a painful mistake to make, but it's exactly the kind of defensive coding trap examiners love to set for you. Don't stress, though. We're going to patch this vulnerability right now.
Here's our roadmap for today. 1. The system crash trap. 2. Core VB data types. 3. Securing strings and characters. 4. Input validation step-by-step. And 5. Scoring high in exams.
Starting with Section 2, Core VB data types, which are the absolute building blocks of your code.
Listen, the Cambridge mark scheme demands absolute precision when it comes to terminology. You might be super accustomed to using the term real to describe numbers with fractions, but Visual Basic explicitly requires the term decimal. You've got to memorize that distinction right now, because writing real on a VB-specific code question is just throwing marks away. And beyond just the names, you really need to grasp the memory footprints. This tells us how efficient our programs actually are. A standard integer takes up a very predictable small amount of space, but a decimal requires significantly more overhead.
And here is why picking the right numerical type is so absolutely crucial. Choosing the wrong one can immediately hog memory or completely shatter your calculations. Integers are fantastic, lightweight little options for counting items or looping through a process. But imagine you're coding a massive banking application. In that scenario, losing even a fraction of a cent because of a memory rounding error, absolute disaster. That is exactly why the decimal data type claims a massive 16 bytes of memory compared to a standard integer. You are literally buying absolute precision for those positive and negative fractional values.
Same rules apply to text. You must never, ever confuse a single char with a string. A char takes up exactly 2 bytes and holds just one single symbol, like the letter A, a $sign, or a hashtag. That's it. A string, on the other hand, is an absolute powerhouse. Just to put its capacity into perspective, a single string can hold up to around 2 billion characters. Think about that. You could practically store a whole library of books inside one variable. And hey, golden syntax rule to remember. Any textual data you pass to a char or a string always has to be tightly wrapped in straight double quotation marks.
Moving right along to Section 3, Securing strings and characters, looking specifically at password logic.
So, imagine you're building a function that checks a new user password. To hand out a definitive pass, the password has to meet some incredibly strict criteria. First, it has to be longer than 6 characters. Second, it absolutely must contain one specific symbol, in this case, a $sign. If it falls short on either of those, bam, it immediately outputs fail. Knowing this logic in your head is great, but how do we practically force the computer to do this using Visual Basic code?
Well, you've got to know the exact VB commands to enforce those rules. First up, the .length property, which checks the character count. Say your password variable is called PW and the user types hello. Calling pw.length hands back the number 5, and the system instantly flags it as too short. Next, we use the .contains method. You call pw.contains and search for that $sign, and it gives you a straightforward Boolean response. True if the symbol is physically in there, false if it's missing. Combining these two methods gives you a highly efficient way to lock down textual data.
All right, Section 4, Input validation step-by-step. Let's finally fix that trap we saw at the start.
Think back to that fatal crash. The system expects a number, but some unpredictable user types a word. If we can't safely drop that input directly into an integer variable without risking an immediate system meltdown, what's our defense? How do we catch this rogue data before it literally breaks the program apart? Honestly, this is an examiner's favorite trap, just waiting to see if you can think defensively as a programmer.
Here is your 4-step type check validation process, and it is an absolute must-know.
Step 1, always store the initial input as a string variable first. By doing this, you're effectively creating a digital quarantine zone. Strings will accept absolutely anything, letters, weird symbols, numbers, without crashing. Step 2, once the data is safely quarantined, you check if the value inside that string is actually a number. Step 3, if it's not a number, reject it outright and prompt the user again. Step 4, if and only if it is a valid number, you then safely convert it and store it in your final integer variable. It's the ultimate shield for your code.
Now, to actually pull off step 2 from that plan, you're going to lean heavily on the isNumeric function. This is a brilliant inbuilt visual basic tool. You just feed it your quarantine string variable, and it outputs a clean Boolean. True if it's numerical, false if it contains text. Simple, right? But you really need to understand its limitations. If you feed isNumeric the value 3.14, it's still going to return true. It only tells you if it's a valid mathematical number. It has no idea how to distinguish between whole integers and decimals. So if your system strictly needs a whole number, you're going to need an extra layer of logical filtering to catch those decimal values.
Let's test this logic out with some normal and extreme data to see our armor working in real time. Imagine our scenario requires a 3-digit number strictly below 501. User inputs 1200. Boom, rejected. It immediately fails the 3-digit length check. Next, the user tries 550. Well, it passes the length check, but fails the value check because it's over the 501 limit. Finally, they input 250. It perfectly passes the length criteria, confidently passes the value criteria, and is safely allowed through to the calculation phase. That right there is robust, multi-layered validation acting exactly as it should.
And finally, Section 5, scoring high in exams, straight from the examiner's perspective.
Look, examiners aren't just looking for a generally right answer. They are actively scanning your paper for command words. If the question tells you to explain a validation technique and you only state the name of it, you're going to lose marks, even if your technical facts are totally correct. Explain demands the why and the how. And keep the golden rule of Cambridge marking in mind. 1 mark usually requires 1 distinct technical point. Please do not waste precious exam time writing a massive paragraph that just repeats the exact same concept using slightly different adjectives.
Here is a massive warning directly from the source material. Do not confuse validation with verification. This is an exam trap just waiting for you to fall into it. Validation is everything we've just covered, checking if data is reasonable, logical, and follows the specific rules of the system, like using that isNumeric check. Verification is an entirely different beast. It simply checks if data has been accurately copied or entered by the user. Think of having to type your new password twice into a website just to make sure you didn't make a typo. They sound so similar, but their actual functions are worlds apart.
So whenever you're faced with a long-form answer, think of this formula as your secret weapon. First, briefly define the concept. Then, show the mechanism. How does the code actually work? Next, you absolutely must apply it to the specific scenario data given to you in the prompt. Finally, state the overarching advantage using examiner-friendly wording. A flawless execution of this formula sounds like this. Validation ensures data is reasonable, using isNumeric to check user input against the 3-digit rule, entirely preventing the scenario's system crash and drastically improving software robustness. See how that transforms a basic thought into a flawless, top-band result? All right, so we've successfully solved the fatal crash. You've got the rock-solid framework for data types, and you've totally mastered input validation. But here is the critical, unresolved problem. You know how to validate these 5 data types perfectly in isolation, right? But how on earth do you trace their values when they are hidden deep inside a complex, multi-layered looping algorithm? Missing that final piece of the puzzle on tracing logic could cost you dearly when you're staring down a difficult trace table question. But don't worry, we are going to build on today's foundation and solve that exact problem in our next explainer. Make sure you subscribe to our YouTube channel at Acely Exams IGCSE so you can keep excelling in your Cambridge exams. See you in the next one.